Welcome to Statistical Inference. Today we are diving into a fascinating and crucial concept known as a complete statistic. If you have ever wondered how statisticians guarantee they have found the absolute best way to estimate a hidden parameter, you are in the right place. We will build this idea from the ground up, starting with a simple real-world analogy and then move into the mathematics. By the end of this video, you will understand exactly what completeness means and why it is the mathematical lock that ensures our estimates are as accurate as possible. Let us get started. Before we look at any math, let us build our intuition with a simple analogy. Imagine you have a digital scale in your kitchen and you want to know the true weight of an apple. In statistics, this true weight is the hidden parameter we want to find. The reading on your scale is your statistic, a summary of your data. Now, suppose you program a custom mathematical formula into the scale to adjust the reading. If this custom formula always averages out to exactly 0 pounds, no matter what object you place on the scale, what does that tell you? If the scale is what we call complete, it means there is no hidden trick. The only way the average is always 0 is if your custom formula literally just outputs the number 0 every single time. There is no useless noise that perfectly cancels out. Now that we understand the intuition, let us translate this into the formal language of statistics. Suppose we collect a sample of data and calculate a summary value from it. We call this summary a statistic and we denote it by the letter T. The behavior of the statistic depends entirely on a hidden true value in the real world, which we call the parameter, denoted by theta. We say that our statistic T is a complete statistic if a very specific condition holds. If we apply any arbitrary mathematical function, let us call it g, to our statistic, and we find that the expected value of this new function is 0 for all possible values of the parameter theta, then the function itself must be 0. In simpler terms, if a transformed version of our statistic averages to 0 no matter what the true parameter is, then that transformation must be multiplying everything by 0. Let us look at the mathematical equation for this condition. The formula states that the expected value of g of t equals 0. Where does this come from? It represents the idea we just discussed, an estimator that averages to 0. In this formula, E stands for the expected value, which is the long-run average of a random process. The term g of t represents any arbitrary mathematical function applied to our statistic t. The equation states that the average of this function is exactly 0, and crucially, this must hold true for every single possible value of the hidden parameter theta. When an estimator averages to 0 like this, statisticians call it an unbiased estimator of 0. If t is a complete statistic, this equation is the starting point that forces the function g to be exactly 0 everywhere. Following our previous equation, if the expected value is 0, the definition of completeness demands that this second formula must also be true. This formula states that the probability of the function g of t being exactly equal to 0 is 1. Let us break down these symbols. P stands for probability. Setting this probability equal to 1 means it is a guaranteed certainty or 100% likely. Therefore, the full mathematical definition of completeness says if the first formula is true, meaning the average is 0, then the second formula must also be true, meaning the function itself is literally 0. There are no non-trivial functions of a complete statistic that can average to 0. If you change the variables and the probability drops below 1, the statistic is not complete. This strict rule is what makes completeness so powerful. Now, how does completeness fit into the broader picture of statistical inference? It is closely tied to another concept called sufficiency. A sufficient statistic is a summary that captures every single piece of useful information about the hidden parameter from the data, leaving nothing important behind. Complete and sufficient statistics almost always go together in advanced statistics. Why? Because of a powerful rule called the Rao-Blackwell theorem, which states that you can improve any guess by combining it with a sufficient statistic. However, to guarantee that this improved guess is the absolute best possible guess, meaning it has the lowest possible variance or error, you need another rule called the Lehman-Sheffey theorem. The Lehman-Sheffey theorem requires the statistic to be both sufficient and complete. Completeness ensures there is only one unique unbiased estimator, preventing any other estimator from ever beating it. Let us visualize how these concepts work together to give us the best possible estimator. On the screen, you see a flowchart representing the Lehman-Sheffey theorem. At the top left, we have the sufficient statistic, which ensures we have extracted all the useful information from our data. At the top right, we have the complete statistic, which ensures there is no redundant noise or wiggle room. When you combine these two properties and pass them through the Lehman-Sheffey theorem, represented by the middle box, you arrive at the ultimate goal at the bottom, the unique minimum variance unbiased estimator, or MVUE. This diagram teaches us that sufficiency provides the raw materials, but completeness acts as the mathematical lock that guarantees our final estimator is unique and cannot be improved upon. Before we move on to the mathematical proof, let us set up a concrete scenario. We are going to look at a classic example involving flipping a coin. Suppose we flip a coin n times. The true probability of getting heads on any single flip is our hidden parameter, which we will call P. We do not know P, but we want to estimate it. Let our statistic, T, be the total number of heads we actually observe in those n flips. Our goal now is to prove mathematically that this total number of heads T is a complete statistic. To do this, we will assume there is some function of T whose expected value is 0, and we will use the properties of the binomial distribution to show that this function must be 0. Let us begin the proof. We start by writing out the standard formula for the expected value of a function of a binomial random variable, and we set it equal to 0. The summation symbol means we are adding up the values for every possible outcome t, from 0 heads up to n heads. The binomial coefficient represents the number of ways to get t heads. To simplify this equation, we factor out the term 1 minus p to the power of n from the sum. We also group the p and 1 minus p terms together into a single fraction raised to the power of t. Because 1 minus p cannot be 0 unless p is exactly 1, which is a trivial edge case, the summation itself must be equal to 0. This algebraic manipulation sets us up perfectly for the final logical step. Continuing from our simplified equation, let us replace that fraction with a new variable, r. What we are left with is a polynomial equation in terms of r. A polynomial is simply a mathematical expression involving a sum of powers of a variable. For this polynomial to equal 0 for every possible positive value of r, a fundamental rule of algebra states that every single coefficient must be exactly 0. The coefficient here is the function g of t multiplied by the binomial coefficient. Since the binomial coefficient is always a positive integer, it cannot be 0. Therefore, the only way for the coefficients to be 0 is if the function g of t itself is 0 for every possible value of t. This perfectly matches our definition of completeness. We have successfully proven that the total number of heads is a complete statistic. Now that we have seen a discrete example with coin flips, let us look at a continuous scenario. This involves measuring data on a smooth scale rather than counting discrete events. Suppose we have a machine that cuts pipes, and the lengths of these pipes are uniformly distributed, meaning every length is equally likely, between 0 and some maximum unknown length, theta. We take a sample of n pipes from this machine. Let our statistic, t, be the length of the longest pipe in our sample, which is known as the sample maximum. Just like before, we want to prove that this sample maximum is a complete statistic. Because the data is continuous, we will use integrals instead of summations. but the core logic remains exactly the same. Let us set up the proof for the continuous case. First, we need the probability density function of the maximum value in a sample of size n from a uniform distribution. This function tells us the relative likelihood of the maximum being a specific value t. To find the expected value for continuous data, we use an integral instead of a sum. We multiply our arbitrary function g of t by the probability density function and integrate from 0 to the unknown maximum theta. We set this entire integral equal to 0 as required by the definition of completeness. Because the terms n and theta to the power of n are constants with respect to the integration variable t, we can multiply both sides of the equation by theta to the power of n divided by n to cancel them out. This leaves us with a much simpler integral. To solve this simplified integral, we apply a powerful tool called the fundamental theorem of calculus. This theorem allows us to take the derivative of the integral with respect to the upper limit, theta. Taking the derivative of the left side simply replaces the integration variable t with theta inside the function. The derivative of 0 on the right side remains 0. This gives us the equation g of theta times theta to the power of n minus 1 equals 0. Since the true maximum length theta is strictly greater than 0, the term theta to the power of n minus 1 cannot be 0. Therefore, the only mathematical possibility is that the function g of theta is 0 for all values. This proves conclusively that the sample maximum is a complete statistic for the uniform distribution. Why do statisticians care so much about completeness? In the real world, when we build algorithms to estimate things like the average lifespan of a car engine or the true effectiveness of a new medication, we want the best possible estimator. An estimator is just a mathematical rule for guessing. We want a rule that is unbiased, meaning it is accurate on average, and has the lowest possible variance, meaning it is highly consistent. Completeness is the mathematical lock that guarantees uniqueness. If a statistic is complete and sufficient, any unbiased estimator you build from it is guaranteed to be the one and only minimum variance unbiased estimator. Without completeness, you might have multiple unbiased estimators, and you would never know if you truly found the absolute best one. We have covered a lot of ground today, so let us summarize the key takeaways. First, a complete statistic ensures that no non-trivial function of the data can average out to 0. It removes any hidden wiggle room. Second, it acts as a mathematical guarantee of uniqueness. If an estimator averages to 0, the estimator itself must be 0. Finally, when combined with sufficiency, completeness provides the ultimate foundation for finding the best possible estimator in statistical inference. It ensures our real-world predictions are as accurate and consistent as mathematically possible. You have now mastered the concept of a complete statistic. Great job!